Yeah, thanks for being here, and thanks for attending my talk, and thanks for inviting me to Paris. Yes, so this is the result, or almost result, of like over 2 years of sweat and blood. And it's gonna, hopefully something's gonna be posted within the next few weeks. Not a complete project, but it consists of several parts. So yeah, hopefully, hopefully like things are, there's a light at the end of the tunnel. So looks like some papers are gonna be finished in the next few weeks. Okay, so what is all this about? It's essentially about this picture that I drew there. So what is that? So I will talk about that a little bit first. So right, okay. So it's all motivated by, certain problems coming from percolation and other lattice models. And I'm gonna present the results, and it is gonna be more high level, so I will not say too much about the proofs, but there are some elements of the proofs that are of independent interest. That's why it's kind of interesting to say a little bit about that. So, okay, so the chemical distance is basically just a fancy name of the intrinsic graph distance. Yeah, so if you take like your percolation cluster, you just look at the as a subgraph and look at the graph distance on that subgraph. Yeah, and the thing is that this is surprisingly tricky to study. So okay, one example where it's well understood is the supercritical percolation. Maybe less surprising because that thing is like just very similar to just the entire space with very few tiny holes, and then people have compared compared and how much this deviates from the entire space. But once you go to critical percolation, you see, wow, this is behaving very differently from the Euclidean space. And there actually not so much has been understood. Yeah, so this was like 20 years ago already from Schramm's article. So, and he already noticed this is actually probably going to be a hard problem to solve. And there's still not really much progress. Yeah. So if you ask, for example, the scaling exponent of the chemical distance, yeah, the intrinsic distance between 2 points of a certain Euclidean distance, then there are some simulations, but like not so many rigorous results. Yeah. So this is all we know here. Okay, so this is this is all that's known in 2D. There's a little bit of work done in high dimension and in hypercube, like something like that, extremely high dimension. And there are some results. But yeah, that's okay. There's another related model was on paper published posted very recently, which is a random planar map version of it. Yeah, and then there's a really nice story that they construct a random metric space that is yes. So it's a metric space, so together with the metric that would correspond to a random map version of that. Yeah. Okay. But today the work I'm talking about is gonna be about the Euclidean space, yeah, which is actually a bit more tricky because there you're not gonna expect as like a nice explicit description as in their work. Yeah, this one is really
if you want, you can turn on the camera.
Ah,
People on Zoom can see you now. You want?
but they're not gonna see my face anyway, I think, because I'm gonna walk around here and there.
Okay, then.
Let me see if I can wait. Okay, I'm a bit over challenged. So I'm a bit Okay. Yeah, just to mention, there are also, I mean, percolation is the thing that people have the most interested in, but like, you know, there are also other models where people have studied something like a chemical distance, and just to list some examples here. Okay, so I'm gonna return back to percolation. Yeah, so this is the picture that you saw on the very on the title slide. Yeah, this is what is drawn here is like a metric ball. Yeah, drawn on top. So I think this is the center. Yeah, and then the distances are like shown in color. So that's the metric ball with respect to the intrinsic metric. And what you see already is like, you know, like there are these places where you have like, you know, tiny gaps, right? So you have to go all the way around here. This is not surprising, right? Because this corresponds to the case where if somebody is able to scroll this a little bit up so I can draw a little something on the blackboard. So there's something like, you know, like there's this thing, there's something like these four so-called forearm events. Huh? Yeah. There are things like these forearm events, right? Yeah, there are these forearm events here where, you know, you have like two open paths and two closed paths going across the, and these things are everywhere. Yeah. On the continuum side, it just corresponds to you have the CLE loop, and then just it has like a self-intersection. Yeah, things like that. Okay. But this already makes the problem actually very interesting, because this is actually an essential feature in the problem we're studying. So yeah, so basically what we want to do is we want a continuum scaling limit of this metric, because, you know, hopefully with the continuum scaling limit, you can you have all the tools for random conformal geometry that you can apply, and then you can hopefully better understand this problem. Yeah. So first of all, yeah, we know the scaling limit of the percolation clusters, what this is as a set. Yeah, this is just given by the so-called CLE6 gasket. Yeah, so that's like, you know, you could describe exactly the cluster boundaries, which is like a random collection of loops, which is exactly what this CLE is. So we want a geodesic metric on the CLE gasket. So this is a particular case of CLE6, but if you know, there's an entire family of CLEs indexed by a parameter kappa, and these should conjecturally at least be the scaling limits of FK models or loop OM models. Okay, some other work prior to that. So as I said, studying a random metric is much harder than studying like a pre problem to that, which is a random measure on the gasket. Yeah, this has been done before. And you can compare this also with what has been done in Liouville quantum gravity. That's a different model of a random metric measure space. Yeah, there again, people have first constructed a measure that was relatively easy, but then you had to do some hard work to construct like also a metric on that space. Okay, so yeah, so the summary of the result in the very high level is like for every non-simple CLE, yeah, this is the range of parameters where you have essentially this phenomenon happening. Yeah, it's actually quite important. So it's actually quite important we in this regime, because the behavior of the CLEs is very, very different in this case, and in the case where you don't actually have these forearms. Yeah. So tools will also be entirely different. So our results are for this regime. And it basically says that there's a unique metric on the CLE gasket. Okay, so what should this unique metric satisfy? So what should this metric satisfy? It should be it's a geodesic metric. It should have, I mean, if it's a metric on CLE, it should satisfy the properties that also characterize CLE. And the result will be these properties also characterize the metric on the CLE. Yeah. So this should be the conjectural scaling limit of the chemical distance in lattice models. And since I mentioned the as an analog, the LQG, I just want to say that this is actually an entirely different problem. Yeah. So for a few reasons that I will mention now, okay, I will mention on the next slide. So maybe I just compare the similarities. Yeah. So I mean, there's like a somewhat standard approach. Yeah. You try to find an approximation for the metric. Yeah. So you want to say that the distance between 2 points is just the shortest, the length of the shortest path between 2 points. But since these things are, think these all these paths are fractal, and you don't even know the dimension of the shortest possible path, yeah, that's exactly this alpha exponent that I mentioned previously in the motivation. Yeah, it's not really even clear how to define the length. Yeah, so that's why we define some approximation of the length. We need to show tightness, and then we need to show that the limits satisfy some of these properties that we want, and that's uniquely characterizable. Yeah. So okay, so far not so surprising. Just a remark. Yeah, as I said, our work is for the non-simple CLE. There has been some work done for the simple CLE, which is entirely different. Yeah. Um, so yeah, so the reason this case is entirely different. One reason is exactly what I drew here on the board. Yeah, because of these forearm things. Yeah, so you have these places where okay, this is like a I mean, you can also switch colors, right? I can draw the same color so that this is open and this is closed, yeah. And then you see that, okay, if you want to travel from one side of the cluster to the other side, and you have these two closed paths here, then there will be these special points where you actually have to pass through, right? So if you want to show tightness, you cannot just say, okay, if it's too long here, I just go around. But notice topology is actually very important. The topology forces you to pass through these points. Yeah, so you really need to understand what happens with your metric near these points. So this is one thing that makes the topology is very unique to this non-simple CLE. Yeah, it's very different to the simple CLE, and it's very different to LQG. Yeah. Okay. Second, that's a challenge that's distinguish it from the random planar map version. For example, yeah, it is things are sensitive to the boundary, right? So if you're, I mean, we know there's like conformal invariance of CLE, yeah, so invariance under conformal maps and stuff like that. But the thing is, if you have like these boundaries which are very fractal, the paths along the boundary, if you distort them, then like yeah, that's so this is everything is very sensitive near these fractal when you change these fractal boundaries. Yeah. And okay, of course, this is just to mention, this is of course not a Gaussian field. So like, yeah, so yeah, so the point I wanted to make is this, yeah, so this problem is actually quite different and yeah, so from the other works.
So the reason why it is very different from the distance in living quantum gravity is because of these boundary conditions.
No, Liouville chromography is planar, right? So the topology has the topology of a plane, right? So, and our topology is obviously not a plane; it's a fractal. Yeah. So our object is more reminiscent of the random version of the Sierpinski gasket, if you can think of that. Yeah. I should put out my clock to see how. Actually, I forgot how much time do I have, by the way? And when did I start?
It was 1 mistake.
Okay. 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 So maybe just yeah. So now I'm gonna slowly go to present the results. Yeah. First of all, I want to define, what I mean by the metric of on the cluster. Yeah. So okay. So obviously, I need to pick some CLE cluster, right? That's like something that corresponds to a percolation cluster. Yeah. So one way of doing that is it doesn't really matter exactly. I just need so okay, maybe it's useful if I draw another picture here. If you put in percolation on a disk, yeah, then you have like these clusters, yeah. So the boundaries are like some loops. They can touch themselves, something like that. Yeah. And then inside these loops, like if so that's what I call by nested CLE, yeah. You have another collection of loops. These are all also non-simple loops, yeah. And basically yeah, so basically the region that's in between here, I mean, this is you get the idea what I mean, right?
You can see it.
Yeah, exactly. So these things are the scaling limit of the percolation clusters. Yeah, it's actually kind of important that we pick out a cluster with fractal boundaries. So you cannot just take the domain with smooth boundary and take the very outermost cluster with the smooth boundary because you always have fractal paths, right? But if you can go along the smooth boundary, then the length will always be 0, right? So yeah, so I just want to say I need to pick out a typical percolation cluster in the interior. Okay, so I pick just some way of picking a cluster, and then I look at the gasket inside. So corresponding to the picture that I drew here. Okay, so one technical point is I want to distinguish. So if we have something like that, yeah, in the continuum limit, these 2 points will become like 1 point, right, in the plane. But I want to distinguish these 2 points. So that's why I will interpret this actually as a metric space where I don't identify these 2 points, but actually I want to pick a metric that gives positive distance to these 2 points. And then I see this as an abstract metric space, which is embedded in the plane. Yeah, in that case, like these 2 points under the project embedding will be mapped to one single point. Yeah, if that makes sense. So I hope this makes sense what I said. Okay, and then for the titles, I also want a topology. Yeah, so I have this abstract metric space here that corresponds to the CLE gasket together with an embedding, and then I have the random metric that I see as a random function on the space, And then I can equip the space with the Gromov-Hausdorff function topology, which is basically just the Gromov-Hausdorff topology for these metric spaces. But I add like some function on these spaces, and I don't know. We just made up that name because we didn't find. I don't think there has been some name for this topology in the literature. So unless you know something. Okay.
Sorry, so instead of taking the points, you have a special function? Is that it?
So I want to show. Huh?
You have the origin, which is fixed.
Okay. I mean, it doesn't really matter. Instead of the origin, I can pick any other point. No. I just need some way of. I just need. I just want to select a cluster of the CLE. Yeah.
And then you have one function with this delta epsilon.
This will be so okay. So if you remember, the strategy was defining an approximate metric, right? And this will be the approximate metric, which will be seen as a function. Okay, strictly speaking, it will be a function on the square of the product of this. Yeah. Okay, so the tightness result is like, okay, I take any reasonable approximation of a geodesic metric, yeah. So just for concreteness, you can think, I mean, this is just an example. The result will be written up in a more general way, yeah. So one simple way of approximating the length, fractal length would be like, yeah, take basically the Minkowski content approximation, yeah. You take an epsilon neighborhood of a path, take the area of the epsilon neighborhood, and you declare this as the approximate length, and you optimize over it. Yeah. Just to give you one concrete example, like yeah. So the result is then okay. I can find a renormalizing sequence so that I have tightness, and any subsequential limit gives you what you want. Yeah, basically a random metric that satisfies these natural properties. Okay, this is good. And then, right, I want to explain what these properties actually mean a bit more precisely. I'm still cheating a little bit. The exact list of axioms is still a bit more complicated, but like, you know, there's in case of keeping things somewhat understandable in it for this talk, I'll just give you the main points of the list of axioms. So geodesic is, I guess, clear. This should be a geodesic space. Yeah. And then, okay, this will be important on the next slide. I want to define internal metrics. Yeah. So if I have like a subregion, then I can define the path length of paths that stay inside these subregions. Yeah. And if you remember, I want a Markovian property. Yeah. So the Markovian property basically says following. So this is what characterizes CLE. Yeah, I give you some region. Yeah, this is the green one is deterministic. And then I want to basically say the CLE inside and the CLE outside are independent. Yeah. This will only be true. I mean, okay. There will be loops that cross the boundary of the green one, right? So what this actual statement is, I look at all those loops that are completely inside the green circle. Yeah. And then if I condition on, so basically the law, so okay, the conditional law of the loops that are in this pink region depend only on the shape of on the boundary of the domain that they live in. Yeah. So another way of formulating it is if I give you the loops that are not completely contained in the circle, the conditional law of the remaining loops depends only on the shape of the boundary where they live in. Yeah.
That metric ball is with respect to this metric that you build.
Oh, this is just some domain. This doesn't have to be a ball. This is
So it is a domain with the usual topology of the complex.
exactly.
Oh.
Yeah. If you think of percolation, for example, yeah. If you think of percolation, it gives you some domain, right? You are suppose you have observed your open-close interface, yeah. So you have like some open-close interface here. Then what is inside is exactly just independent percolation in here again, and this is just a CLE analog of it, yeah. Yes. So and then the natural thing you want for your metric is that the metric in here, because it should really just be determined by the CLE config the loops in the pink regions, right? So it should actually be independent of the metric outside, and this is exactly the statement that we want. Yeah. So if you condition on the shape of the pink region, then everything outside and everything inside are conditionally independent. I think this is the most mind-fucking thing to get your head around, but like, yeah, among the list of axioms. Okay, and then okay, this is less surprising. Conformal covariance. Well, yeah, of course, if you scale things, right, then there will be the scaling exponent here. This is exactly this unknown exponent alpha that I mentioned in the that introduction. There should be such an exponent, so that if you conformally distort a path, then the length like scale like that. Okay. Okay, now so I've told you what the list of axioms is, and then the result is basically, okay, this list of axioms characterize the metric. Yeah. So there's a unique metric up to a constant such that this is satisfied. Yeah. And by just a comment, the uniqueness also implies, you can see that with like a short argument, that this scaling exponent alpha exists and is unique. Yeah. You don't know what it is though. So oh, by the way, for those of you who know, like I know we're in France, so people might know about the stable gasket. Yeah, there the exponent is explicit because the stable gasket, yeah, that's the random planar map version, has an explicit description. Yeah, but that's really because the random planar map version has so much more symmetries than the Euclidean case. Yeah. So in the Euclidean case, this is, yeah, like I don't think there's gonna be any magic that gives you some nice formula for this exponent. Mm. I mean, oh no, it's not optimal. It's somewhere in between these. So all right, this is just if you follow the cluster boundary. If you follow the cluster boundary, that's that's the upper bound. You cannot, I mean, you can always follow the cluster boundary to find the shortest path, right? Yeah. Yeah. Okay. This is another thing that seems to have not too much to do with what I was talking about, but this is actually a very important technical tool, and I want to present it because it's actually of independent interest and a very useful tool if you do anything with CLE. Yeah. So this is one way of phrasing to what extent CLE configurations in different regions are approximately independent. Yeah, so the setup is basically, okay, I take two, I look at basically, maybe I can do the full thing here. I look at some region, yeah, this is the outer square in this case, yeah. I look at all the loops that intersect the complement, and then because they cross in and out this boundary many times, so the way of observing them is okay, extend them a little bit until they hit my inner square, and then there are only finitely many unfinished strands left, and I look at this remainder, yeah. So I get like some domain with a number of marked points. I want to say, okay, what is the law of the remainder of the CLE after I've observed what I have drawn there? And the result is, okay, first of all, it's important to notice, well, first of all, they can hook up in many different ways, yeah? So, and we want to understand the probabilities of how they hook up, yeah, and the result is like, okay, this is actually just the conformal invariant, yeah. So this is you can see this as a marked domain together with some external wiring of the marked points, and this is the law of the conditional law of the remainder is just the conformal invariant of this marked configuration with this external wiring. Yeah. And we went a bit further and gave a more systematic approach to this. So first of all, in the case of if you have just 4 marked points or 2 chords, yeah, so basically you have this picture here. Yeah, so you have some random domain with a few marked points here. If there are only 4, this was studied before in another paper. Yeah, there you have these 2 possible patterns, right? You have this possible pattern. So okay, suppose that this is the exterior link. Yeah, then you have 2 possible linking patterns here. One is this one. The other possibility is they link in this way. And the probability which one occurs has been explicitly computed in these papers here. This is what we call the bicaudal CLE law. And then if you have more marked points, the result is basically, yeah, if you have more marked points here, if you condition on all the strands, all the other strands, then the remaining 2 chords have exactly this bicaudal law. Yeah. This is the yeah, and so this we show that this actually characterizes this law on these n tuples of chords. Yeah. So we give it a name that we call this a multicaudal CLE. So the result is like, okay, if I give you any marked domain and with marked points and some exterior link pattern, then this multicaudal CLE law exists and is unique. Yeah, and the law is continuous when you move around the marked points. And this is actually quite nice because this should just, okay, I will say something about that. Maybe I'll say that first. This should just correspond to the scaling limit of, if you have, I mean, okay, the percolation case doesn't really matter because the percolation, it does matter, but the percolation case doesn't really see the external wirings, yeah? But if you have like some FK model, yeah, you have like, or ON model, yeah, and you have some boundary arcs here, yeah, then it actually does matter how these external arcs are wired outside, right? Because it affects the number of clusters, right? that like this is now one cluster. If you don't have this external wiring here, then this would be two clusters, right? So yeah, so this multichordal CLE law should really just be the scaling limit of the FK and ON loop models where we have such type of boundary conditions. And then there's a conjectural formula for what the actual hookup probabilities should be. Yeah. Okay. And another nice remark is that that if you take if you condition on a certain hookup pattern, yeah, if you condition on a specific hookup pattern, this thing has a name. This is what is called a multiple SLE in the literature. Okay. Okay, so what we have not proved is this conjectural connection probability formula, but we have proved that the connection, these hookup probabilities are always positive and for each possible linking pattern, and they are continuous in the mark point configuration. Okay, why is this useful? This is just a remark. If you ever want to work with CLEs, this is kind of useful because you can say like, well, if you want to know the law of the CLE in this region, then you can compare it somewhat to CLE in this region where you change your CLE slightly a bit. That you just slightly resample them so that these are actually linked together. Like, well, okay, you could ask, why do I care? But actually, yeah, if people have worked with these things before, they will appreciate why they would care, because these things are actually could be quite annoying to work with. And so having these little tricks to compare different this and this picture can be actually quite useful. Yeah. Okay, how much time can I have? Okay. Okay. So maybe I have like 10 more minutes or something so that I can just comment briefly what one needs to prove. Yeah. As I said, this is more like an overview, just to give you some idea. Yeah. So first of all, I mentioned this before. You really have to deal with these 4 points. Yeah. Yes, because all your paths that travel through the cluster will need to pass through these points. Yeah. So we need to understand the length between such a region. Yeah. Okay. And this is actually how we define the normalizing constant. Yeah, to let it be the median of that thing. Okay. And then the main step is basically what we want to do is we want to do like a chaining argument. Yeah. Basically in the spirit of Kolmogorov's theorem. Yeah. So we want to do a chaining argument to prove Hölder continuity. Yeah, because if you have Hölder continuity, then you have tightness. Yeah. And then for that, you want to show that this thing has a super polynomial tail. Yeah. Okay. How to do that? Well, you use independence, right? So in some sense, okay, you show that you use some symmetries to show that this holds for some power, and then you want to improve this power using independence, because if you have such a thing. So this is basically just, it's a picture on the right. It's just I pick one particular like pocket here around among this thing, yeah, and then the CLE in this green region is just like so the loops in this region conditionally on the outside is just the CLE in the green region, yeah. So it will look like something on this picture. Yeah, so you have this green bubble here, and then you have a collection of loops in here, and then you see, okay, actually you see the same picture once on this side and another one on this side, because this is a region that lies between two CLE loops. This is a region that lies between two CLE loops. And if you believe these two sides are approximately independent, you will have basically you get like twice the chance to get through in short distance. Yeah. Somehow this is basically the idea, but the thing is like, the approximate independence is a bit tricky because, you know, if you condition on one side, remember the Markov property is actually saying if I condition on the loops here, then the remainder is the CLE in this fractal region here. But, you know, this fractal region, of course, depends on the shape of the loops, and the path lengths are very sensitive to the shape of the loops. So this adds actually quite a lot of pain and to really work with. I'm not going to go into much detail here, but this is like, yeah, this is what you should keep in mind. What's the intuition behind the proof should be. Yeah. Okay. Okay, just a few words about the uniqueness. So the idea is the following. So suppose you have two CLE metrics. Yeah, you want to say they're equal. Yeah, and then essentially it's there's like some law of large numbers phenomenon going on. Yeah, so okay, so there's like some, so CLE should locally look the same everywhere. Yeah. So and then so because these two things are geodesic metrics, yeah. So you have like so say you have 2 points, and you have a geodesic with respect to one of those metrics, for example, yeah. And then if you look around each point, yeah, in a small neighborhood, so yeah, this should look the same everywhere, right? So this, if you look at the ratio between these two metrics in each of these small balls here, they should approximately have the same ratio everywhere. And if you also think like, oh, this should be somewhat IID everywhere, then you could intuitively guess that there should be some law of large numbers phenomenon going on. And this is indeed what happens, yeah. And then you'll see, okay, actually this has to be a constant. The ratio has to be constant. Again, this is the intuition. Making this precise is a bit more difficult. Maybe I'm not gonna go too much into detail here, just a few comments. What you need to do, you need to find some, somehow annuli that are independent, and then use some independence across scales, and then, you know, yeah, anyway. Okay. Okay, I did well with the time. Oh, actually, I'm a bit early. I rushed a bit too. That's okay. I have one more slide just to say a few comments on some related questions that relate to that. So first of all, actually, we are planning to do that already, because we have constructed our nice metric. Then we obviously we want to go back to our initial problem. We want to show that the metric on percolation converges to our metric, right? And we did actually good amount of work for the preparation for that, because we have shown already we have a unique metric that's characterized by a list of axioms. So what we need to do is like show that the metric on percolation is tight, and the subsequential limits satisfy this characterization, right? So yeah, so this seems fine, yeah, and we are in the process of doing that. Also, our framework is a bit more general, actually. So we study a bit broader class of metrics, and there's one particular metric that people are interested in. This is the effective resistance. This is also related to random walk on the cluster, and people know this as the ant in the labyrinth problem. So that is also quite nice to study. So actually, we have now rewritten the tightness paper in a general enough term that it covers also this metric. So, but then you still have to prove uniqueness, and then you want to also prove the scaling limit of the effective resistance on percolation to this thing. So yeah. Okay, and then you can ask some more, hypothetical or how to say hypothetical questions like, okay, how much can you actually say about the exponents, right? So all the exponents, as opposed to the random planar map version in the Euclidean case, all these exponents are not known. And not really, really nothing is known about them except for the trivial bounds. So how much can we say about them? And of course, we want to do the random planar map version, right? Because this should give us exactly the stable gasket. Yeah. So they have constructed this random metric space, and they conjecture this should be in a CLE on an RPG, but like one needs to prove that. Okay, so yeah, thank you very much.
Question or comment?
You remember what was the Alexander-Orban conjunction?
Oh, it's about the spectral dimension of the random walk on percolation. Yeah, it's another exponent. It's not the alpha that was on the slides, but it's a different exponent that's related to the effective resistance here.
And is there a fractal dimension of your metric space? And is it the same as the one?
Yeah, it should just be the alpha that, or is it alpha? It should be something with this alpha. Yeah. No. Yeah. Something like that. I need a few minutes to figure out, but it should be something with that. Yeah. It's either alpha or 2 minus alpha, or it's like something 1 over alpha, or maybe 1 over alpha. Yeah, if I say something in 10 seconds, it's gonna be wrong. So that's why. But it should be something with this alpha. Yeah. 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 There is a measure that's actually this has been done in a paper by Gaban Peter Schramm, and so there is I think I've had this somewhere on a previous slide. I think when I was mentioning some other related work. So there is like there's this measure. So before you construct a metric, you first do an easier problem that's constructing a measure, and okay, what has not been done is yet identifying this measure with the Peter Schramm limit, but it should be not too much work to say that their measure is the same as this measure. So yeah. Yes. Yeah. If you, because of some law of large numbers thing, it should be.
Your comment? Anyone doing financial consume? No? Okay. So we can thank the speaker again.